Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we are going through the paper on physics of materials. Now, in this paper, the chapter with which we are dealing is bondings in solids, and in particular the X-ray diffraction which is being used not only to understand bonding and also to know the atomic arrangement in solids, because there is a famous thing, structure and bonding, whether structure decides bonding or bonding decides structure, they are highly interconnected. The lecture number 14, and the contents of this lecture are Bragg's law, with which we are discussing in the previous lecture also to some extent, types of X-ray cameras used, rotating crystal method, calculation of interatomic spacing, Debye-Scherrer camera, and powder diffraction. Now, we are again having a relook at Bragg's law to gain a better understanding. Now, what is Bragg's law? The father and son, the W. H. Bragg and W. L. Bragg, they showed that when you have a crystalline plane in a solid, you have got planes of atoms, you have got a crystalline plane. A plane is one which contains or carries atoms, right, is a crystalline plane. There is another plane, another plane. Now, supposing X-ray beam is incident, right, on this plane, you see a plane, you see this plane, X-ray beam being incident on this plane, it is the theta is the grazing incidence, right. This is a reflected or diffracted angle, the theta, both theta should be same. So, the incident beam, reflected beam, right, incident on or falling on the top plane. Secondly, now you see the another beam, right, you got another beam here, then it is incident on the second crystalline plane. Now, the beam is reflected. Now, you should notice that when a wave is passing in a pond of water, you have a beaker or some amount of water contained in a vessel, you drop a small stone, you get a wave pattern, right, you get a wave pattern, you see the ups and downs or the the trough, and you have got a this thing and a trough here and right, and so this is a undisplaced thing, and this you got a trough here and okay. Then wherever you got this kind of thing, and you should have a crust here and trough here, right. A crust means a crust, right. A crust means a crust. You go to the beach, what do you observe? You see a wave coming nearer to you, you are sitting on the sand, you are in the beach and you feel that the water will come to your feet or come and touch, but you see the next wave that is coming, it destroys the first wave. Then you can see the destructive interference when you go to the beach, right. Similarly, here, so if a crust meets a crust or a trough meets a trough, there will be a constructive interference. You have a trough meeting a trough or a crust meeting a crust, there will be a constructive interference. So, if a trough and crust meet, trough means it is a minus A, right. If A is the amplitude minus A, crust is plus A and minus A will be equal to 0, and plus A and plus A will be 2 A, minus A and minus A also minus 2 A. What intensity will be the square of the amplitude, it is either plus 2 A square or minus 2 A square is the material, the intensity is the same. So, a crust meeting a crust or a trough meeting a trough will give rise to a constructive interference, that you should all remember as students of science or students of applied electronics. We are talking about electromagnetic waves, right, wave propagation. So, a crust meeting a crust or a trough meeting a trough will give rise to constructive interference. On the other hand, a crust meeting a trough will lead to destructive interference, that is what we are precisely telling here. You see a crust here and a crust here, the crust and crust they meet, right. So, then a crust is meeting a crust, a trough is meeting a trough. So, a crust meeting a crust or a trough meeting a trough, they will lead to constructive interference. So, the path difference should be integral multiple of lambda. If it is instead of n lambda, if it is n plus half into lambda or lambda by 2, what does it mean? Lambda by 2 means a crust is meeting a trough, right. Then there will be destructive interference, the displacement will be 0, the displacement will be 0. So, your path difference should be lambda. Why should it be lambda path difference? The path difference is integral multiple of lambda, n lambda, lambda, then only a crust and a trough and a trough will meet. So, you have this path difference here, as I told you in the last lecture, this is the path difference. What is path difference? Extra distance travelled by the second beam compared to the first beam. You see here, this is the distance travel, right. Here also distance travel will be, you have here up to this distance, right, the same distance travel, both are the same. Similarly, from here onwards, the distance travel will be equal to distance travel. Now, what about you compare the first ray or the first wave and the second wave? The extra distance traveled by the second wave is this much, right. What is this much? This is lambda by 2 or lambda by 2, this is d sin theta, as I told you in the earlier lecture, this is d sin theta, this is d sin theta, that is 2 d sin theta. If this is lambda by 2, as I show here, this is lambda by 2, this is again lambda by 2, then that means this is lambda, right. If it is lambda means there is a wave here, another wave here, right. If this is lambda, the path difference is lambda, then there will be a constructive interference, right. So, you have the wave here, if this is lambda by 2, right, this is lambda by 2, if this is a full wave, this is lambda, right. The distance between this point and this point is lambda, this is lambda by 2 and this is lambda by 2, this is lambda by 2. So, this is the additional path travelled by the second beam compared to the first beam. The additional path travel is lambda, right. In this case is lambda. In general, if it is n lambda, then that will lead to constructive interference. That should be understood by all the people who are studying waves, right, whether it is X-rays or ordinary rays. You have studied diffraction of ordinary light or diffraction and things like that. You study optoelectronics, right. In all fields, when you are talking about waves, then you should be knowing about amplitude, frequency and the path difference and so on. For constructive interference, the path difference should be n lambda, that should be equal to, in this case, 2 d sin theta, because this is d sin theta, this is d sin theta, and so 2 d sin theta should be equal to n lambda. That is the so called Bragg's law. What do you get from Bragg's law? If theta is known, the grazing incidence is known, if theta is known, then if lambda is known, if you are using a copper target, you know the lambda is 1.541 angstroms, then lambda is known, theta is known, d can be calculated. What is d? D is the interplanar separation, the distance separating this plane and this plane is so called interplanar separation. Distance separating the two atomic planes can be determined. This combined with A, the lattice constant. Apart from that, the HKL, we will be seeing the next chapter, the chapter on crystal structure, more about HKL, the Miller indices or the indices which are used to define a crystalline plane. If you know HKL as well as D, A can be determined. What is A? A is the lattice constant. The lattice constant of the crystal structure can be determined using the Bragg's law and the other things. So, let me now go to the problem in which what we do is use the simple Bragg's law in order to calculate the value of theta. It is a very simple substitution. What I am doing, I am using this law, right, n lambda 2 d sin theta, you got 2 d sin theta with n lambda. The problem is as follows: calculate the Bragg angle for the first order diffraction maximum, given that lambda I am giving 0.3 angstroms and d is 1 angstroms. Now, d is 1 angstroms, this is d, right, d is here, this is 1, this becomes 1 unity. So, what remains is 2 sin theta will be n lambda. I have told the order also first order, n is also unity, n is unity, d is again unity. So, your 2 sin theta or sin theta will be simply lambda by 2 d, right. I have given d, that is again 1. So, lambda by 2 becomes equal to sin theta and lambda also given 0.39 angstrom unit. So, substitute lambda here and get the theta. So, sin theta will be 0.239, d is 1, 2 into 1, that is 0.195, because n is 1, d is 1, hence theta becomes the equal to 11.18 degrees. What is theta? Theta is the angle at which the X-ray beam is incident with respect to the plane of the crystal. It is called the grazing angle, right. It is not angle of incidence as you normally do in the reflection of the light beams. It is called a grazing angle, that is the angle that makes by the X-ray beam with respect to the plane of the crystal. This is theta, right. That theta value will be 11.18 degrees. That is what you get from the problem. Now, let us go through some of the primary uses of X-rays and also the limitations you can read in detail. So, X-rays have made it possible to measure the distance between successive atomic planes. As I told you, 2 d sin theta and lambda, d can be determined, right. And positions of atoms or ions within a crystal, allowing for the determination of the crystal structure. Apart from the Lowe method, there are other methods which we will be dealing with. From that, it is possible to study the crystal structures in a greater detail. XRD, that means X-ray diffraction, can only work with crystalline materials, non-crystalline or amorphous. For glasses, you cannot pay X-ray diffraction, because the atoms are arranged in a periodic manner. The atoms should be arranged in a periodic manner, then only X-ray can be used. So, that is one of the limitations. Okay. Powder XRD, which we will be dealing with in a moment. Powder X-ray diffraction can be used to fingerprint minerals without any prior knowledge of crystal structure or symmetry. The minerals which are contained in a material sample, the minerals can be known using powder XRD. Okay. Then the phases that comprise less than about 3 to 5% weight percentage of a sample will not be detected using bench top XRD. There are some limitations. Relative proportions of mineral mixtures can be obtained by comparing diffraction line intensity. Line intensity law remains what? The amount of atoms present of that particular species is large. That is the reason why a particular intensity is very high, right. If the amount of the material present is lesser, means the intensity also lesser. Mixtures of phases with low symmetry will be difficult to differentiate due to the larger number of diffraction peaks. These are some of the limitations. We will pass on to types of X-ray cameras used. There are many types of X-ray camera to sort out reflections from different crystal planes. The cameras which are used to study X-ray diffraction are listed here. We talked about the Loewe method, Loewe photograph, Loewe pattern we saw. Apart from Loewe pattern, we have the rotating crystal method, wherein the crystal will be rotated, right. The rotating crystal method and the powder photograph, which use the powder is kept in a so called Lindemann tube. So, therefore, we will, having discussed about Loewe method, we will restrict now ourselves to the rotating crystal method and the powder photograph. Now, let us make a comparative study of the different methods. The methods are the Loewe method, the rotating crystal method and the powder diffraction. Now, what do you do in the Loewe method? The Loewe method, as I told you, can be used to study the orientation of the crystal alone. The crystal structure cannot be evaluated, that is not a good method. It is not a method practically which can be used to study the crystal structure. What do you do in that case? You make use of a single crystal, that should be remembered. In the Loewe method, the orientation alone can be studied. You have to make use of a single crystal. Then the X-ray beam that is used is a polychromatic beam. It is not a single wavelength, it is a polychromatic. It is not monochromatic, it is polychromatic. Then the angle also is fixed, a fixed angle. Whereas, in the rotating crystal method, you can determine the lattice constant, as we will see later. Then you again use a single crystal, as I told you just now. You have a monochromatic beam and the angle can be varied, the variable angle. In the powder diffraction, you will be using powder. So, using which you can determine the lattice parameters. It is a polycrystal, the powder, right. Polycrystal means you have got very many crystals, not a single crystal. Then in this case, you are using a monochromatic beam, right. It is a monochromatic beam, here also monochromatic, right. Then variable angle. Okay. So, now we will discuss about the rotating crystal method, then we will move on to the powder diffraction. In the rotating crystal method, as the crystal rotates, because the words rotating crystal implies the crystal is being rotated, sets of lattice planes will at some point make the correct Bragg angle. So, the Bragg angle, you have got the theta, that is the beam is incident on a crystalline plane, gets reflected, right. If it is not so, the lambda, d and theta, they should be in such a way that these three should be satisfying the Bragg's equation. Okay. Then only that crystalline, the diffraction that is coming that from that crystalline plane will be the diffracted beam will be seen in the X-ray film. So, sets of lattice planes will at some point make the correct Bragg angle for the monochromatic incident beam, and at that point a diffracted beam will be formed. So, a diffracted beam will be formed at a particular point depending upon d, theta and lambda. Okay. Lambda is fixed, right. Here a monochromatic incident means lambda is fixed. So, the rotating crystal method, a single crystal is used again, lambda is fixed, you are using a single crystal. In the rotating crystal method, a single crystal is mounted with an axis normal to a monochromatic beam, a crystal is fixed. A cylindrical film is placed around it and the crystal is rotated about the chosen axis. The crystal will be rotated along in the, as you see in the next picture. Now, you have got incident beam. Okay. You have got a source, X-ray source. So, the X-ray radiation will be coming here. You are using what a monochromatic radiation. So, the radiation will be like copper K alpha, it is 1.54 angstrom coming from copper target. You can have a copper target. From the copper target, you get an incident X-ray beam with a wavelength of 1.541 angstrom unit, that will be incident on this crystal. What is that crystal? It is a single crystal, right? It is very important. What is single crystal? It is different from a polycrystal. Or the atoms are arranged throughout the whole volume in a repetitive pattern, right? You have got atom here. So, if the distance is A to A3 and so on, A here to A and so on, in all the 3 directions, the atoms will be arranged in a periodic manner. It is a single crystal. Okay. So, you are using a single crystal, right. The crystal will be rotated in this direction, right. The crystal is kept here. So, it will be rotated, right. It will be rotated, and various crystalline planes will come in the direction. The incident beam will meet various crystalline plane depending upon the angle at which the incident beam meets the crystalline plane. If it satisfies the Bragg condition, then the beam will be reflected or diffracted. So, you have a cylindrical film, right. You got a cylindrical film, okay, that is important, right. A cylindrical film. So, on which you have a plane. So, the light ray will be, the X-ray will be incident, okay. It undergoes a diffraction. On the cylindrical film, the spot will be observed, will be obtained. So, the reflected beam, you see the reflected beam here coming, okay, from the incident beam, X-ray beam, which is incident on a single crystal, you get a reflected beam. When will you have the reflection? The reflection will be coming, you have a single wavelength, you got a single crystal, the reflection will be coming if it satisfies the Bragg's law. Lambda is fixed, okay. N lambda 2d sin theta is known, and so depending upon the crystalline plane and the theta will be. So, you get a reflected beam. Okay. So, again I have to go back to Bragg's law in a greater detail, because the diffraction depends upon the diffraction depends upon the crystalline plane. If it satisfies a particular, suppose the diffracted beam, the point will be, you get a point here. For this plane, the point will be at some other place. Okay. You get a series of points, or depending upon the rotating crystal method, you got a cylindrical film, you will be getting arcs. Okay. The lattice constant of the crystal can be determined with this method. The important point, what is the difference between the Laue method and this method? The Laue method can give only the orientation of the crystal and not the lattice constant. The crystal structure cannot be solved. With the Bragg's law, the D is known, then A can be determined, right. What I will show or do a problem is to show that how A, what is A? The lattice constant, right. In all the books on crystal structures, the lattice constants of all the elements in the periodic table, you take iron, cobalt, then rhenium, ruthenium or gold or copper, all the elements in the periodic table, the lattice constant, either they will be face centered cubic or body centered cubic or simple cubic or hexagonal close packed structure or rhomblohedral or whatever be the thing, whatever be the crystal structure, the lattice parameters will be, you will have A, C and so on, right, or B also will be there, seen orthorhombic. So, A, B, C and so on. So, the lattice constants can be evaluated using the rotating crystal method. The lattice constant of the crystal can be determined with this method. For a given wavelength lambda, if the angle theta at which the reflection occurs is known, D can be determined using the Bragg's law. So, using Bragg's law, D can be determined. If you know D, then you can make use of this relation. What is the relation? D is equal to A by, A is the lattice constant, right, A by h square plus k square plus L square. What are h, k, L? They are the so called Miller indices, which we will see in detail in the next chapter, where h, k, L they refer to, if I put 1 1 0 or 1 1 1 or 2 1 1, they refer to different crystalline planes, right. You got a crystalline plane, you may have another plane like this, another plane like this. What is a crystalline plane? A plane containing carrying atoms or containing atoms. A different crystalline planes can be indexed using the numbers 111 or 211 or 210 given by Miller. Actually, Miller, the credit should not go to Miller, it should actually go to Miller's teacher who taught Miller as to how the different planes can be indexed. Okay. I will come to that in a greater detail the lectures to come. So, if you know the Miller indices HKL and D, A can be determined. That is what I would like to tell you from this slide. And 2D sin theta and lambda is the well known Bragg's law. So, D can be determined using Bragg's law. The known D can be substituted here, and knowing HKL you can determine A. Okay. That is the sum and substance of this slide. So, this is the rotating crystal method, as I told you. You got again the incident beam, you have got the cylindrical film, the single crystal is kept here. The reflected beams are located on the surfaces of imaginary cones. By recording the diffraction patterns, both angles and intensities are coming from various crystal orientations, one can determine the shape and size of the unit cell as well as the arrangement of atoms inside the cell. The arrangement of atoms inside the cubic cell or hexagonal close packed cell, the arrangement of atoms and the lattice parameters, all these things can be obtained. There is a pattern that we are obtaining in the case of the rotating crystal method. The dots are shown here. The cylindrical film can be removed after the experiment is over. It is made flat, and in the film the dots will be seen. The dots that you observe here can be seen on the film. So, this is the point here through which the X-ray is passing, right. So, the cylindrical film can be, it becomes a flat film. From the dots you can determine all these things, right. So, now let us move on to the powder method. Now, what is powder diffraction? A powder diffraction means instead of a single crystal you will be using powder. Powder means what? It is not a, you got different crystals, it is a agglomeration of different crystals, right. Not a single crystal, it is a collection of different tiny crystals, okay, different powders or tiny crystals. Here you need not use again you use you can use a single wavelength. It is not a single crystal, right. The important thing is not a single, there is no need to rotate it, right, because there will be always certain planes which will satisfy the Bragg's law. There will be crystals and crystalline planes at an orientation for which diffraction is permitted, and that means the Bragg's law is satisfied. Here a monochromatic X-ray beam is incident on a powder or a polycrystalline sample. This is not a single crystal as we did in the earlier method. The powder beams, it is a polycrystalline sample, right. A polycrystalline sample, you are using a single wavelength, a monochromatic X-ray beam is used. So, for a given lambda, depending upon the theta value, because it is a polycrystal, right. So, one crystal may have orientation like this, the X-ray beam is incident. So, it will be getting a reflected, and another crystal may be having this kind of incidence. Okay, the X-ray beam will be coming here and that will be getting reflected at some other directions, and the angle will be different, right. So, useful for samples that are difficult to obtain in single crystal form, the powder method is used to determine the lattice parameters accurately. Lattice parameters are the magnitudes of the unit vectors A, B and C, which define the unit cell. As I told you, A, B, C, if they are different, they are orthorhombic. If A and equal to B, not equal to C, is called the tetragonal unit cell. For every set of planes, one or more crystals will be having the correct orientation satisfying the Bragg angle or a Bragg's law. So, that you get the diffraction pattern, right. Each diffraction line is made up of a large number of small spots, each form a separate crystal. Each spot is so small as to give the appearance of a continuous line. Let me now complete the powder method. The summary of this lecture will be as follows. We have been seeing the different X-ray diffraction methods. So, the methods which we have seen are the Loewe method, the powder diffraction method and the rotating crystal method. The lattice constant of a crystal can be evaluated knowing D and HKL. We had the relation. So, if you know D and the Miller radius is HKL of a plane, then the lattice quantity A can be determined. In the rotating crystal method, a single crystal is used, right. These are the points that I would like to tell you from today's lecture. The questions are as follows: what is Bragg's law? The question number 2, what are the primary uses of X-rays? Question number 3, distinguish between the rotating crystal method and the powder diffraction method. With this, we come to the end of this lecture. The rest we will see in the lectures to come. Thank you.